Welcome to This Explainer. Today, we're unpacking the exact architecture powering the generative AI revolution, denoising diffusion probabilistic models. If you've ever wondered how a simple text prompt turns into a photorealistic image, a high-definition video, or even a completely original piece of music, well, you're in the right place. We are going to break down the science, the math, and the engineering behind the absolute most important framework in modern artificial intelligence.
But before we look at any code or architecture diagrams, I want you to internalize this fascinating hook. To create flawless, stunningly detailed data from scratch, the absolute best trick we found is to first completely obliterate it. I know, it sounds entirely backwards, right? To build, we must first destroy. Keep that paradox in the back of your mind as we go through today's concepts.
Here's our roadmap for today. We'll explore generative AI's missing piece, the forward and reverse processes, why diffusion actually works, building and avoiding pitfalls, and finally, scaling diffusion for production. Section 1. Generative AI's missing piece. Just a few years ago, if you wanted to build a generative model, you basically had two main choices. And honestly, both came with massive headaches. First, you had GANs, or generative adversarial networks. They pitted two neural networks against each other in a minimax game, and while they produced sharp images, they were about as mathematically stable as a house of cards in a hurricane, and they'd often just diverge completely. On the flip side, you had VAEs, variational autoencoders. These were much more stable to train, but because of how they compressed and reconstructed data, they produced notoriously blurry, soft samples. The industry was desperately searching for a training objective that had a single, stable loss, meaning no stressful minimax games, but still delivered that state-of-the-art, crisp quality. It's really wild to look at the timeline of how we finally found that missing piece. Back in 2015, Sol Dickstein proposed a theoretical Markov chain model based on non-equilibrium thermodynamics. It was a super neat idea, but largely just an academic curiosity at the time. Then, in 2020, Ho, Jane, and Abil published the landmark DDPM paper. They cleaned up the math and showed you could actually simplify the loss down to just predicting noise. Boom! Suddenly, in 2021, these models were beating GANs. By 2022, Stable Diffusion brought the tech to the masses. And today, in 2026, it is the undisputed, universal substrate for all media generation. Section 2. The grand illusion forward and reverse. The first act of this illusion is what we call the forward process, mathematically denoted as Q. Imagine taking a perfect, high-resolution photograph. In the forward process, we deliberately take that pristine image and progressively ruin it by adding pure Gaussian noise, step by step, typically over 1,000 tiny steps. By the end of this process, the original image is completely gone. It's nothing but pure, unadulterated static. Crucially, this is a fixed mathematical process. There's literally no machine learning happening here yet. We are just predictably destroying the data. Then comes Act 2, the reverse process, denoted as p theta. This is where the magic actually happens. We train a neural network, which is usually a unit or a transformer, to act as a masterful art restorer. It looks at a noisy image at a specific step and learns to perfectly guess the exact noise that was just added. By predicting that noise and subtracting it out, the network takes a step backwards. Iterate this process from pure static all the way down to step 0, and it perfectly reconstructs stunning data from absolute randomness. It's incredible. All right, let's translate some of that intimidating academic jargon you might hear into plain English. When researchers say adding noise, they just mean that forward process we just talked about. Denoising is the reverse process. When they talk about the noise ladder or the beta schedule, they're simply talking about exactly how much noise is added at each of those 1,000 steps. Knowing these translations makes navigating the whole diffusion space infinitely easier. Section 3. Why diffusion actually works. So why does this roundabout method work so incredibly well? Well, the crucial point is that this process takes an impossibly hard problem, generating a perfect image from scratch, and breaks it down into hundreds of trivially easy problems. At step 1,000, cleaning pure noise is basically a random guess, which is easy. At step 1, cleaning a near-perfect image is just a minor touch-up. Plus, predicting noise is mathematically equivalent to something called score matching, meaning the model is essentially taking a guided walk toward realistic images. But the absolute best part is the math. The incredibly complex variational lower bound equation elegantly collapses down into a basic mean-squared error calculation. You are literally just calculating the difference between the noise the model guessed and the noise you actually added. That gives the model a massive, incredibly stable gradient signal during training. I absolutely love this little piece of machine learning history.
In the original 2020 paper, when deriving that complex math down to mean squared error, there were these messy mathematical coefficients left over attached to different time steps. Jonathan Ho and his team decided to just drop those coefficients to see what would happen. They literally called it the simple loss. And incredibly, by making the math theoretically wrong or less rigorous, the actual visual quality of the generated images improved. Sometimes elegant simplicity just totally beats rigorous complexity.
Section 4. Building and avoiding pitfalls. When you're actually building this, a huge challenge in the reverse process is that your neural network has to know exactly what time step it's currently trying to denoise. The noise profile at step 900 looks very, very different from step 10. So you have to feed time into the network. Now, for basic toy models, you can use sinusoidal embeddings, basically sine and cosine waves, kind of like how transformers read positional data. But if you're building for production, you have to use film conditioning. This technique takes that time embedding and projects it as a scale and bias across every single channel in your network, ensuring the model's behavior fundamentally shifts depending on how noisy the image actually is. So, if you're building a diffusion model right now, consider this your survival guide. First, watch your noise schedule. The original paper used a linear schedule, but switching to a cosine schedule often dramatically improves image quality without adding any extra compute. Second, never use raw floats for your time steps. They are just way too fragile. Always use a proper embedding. Third, while predicting the raw noise, which is called epsilon prediction, is standard, moving to V prediction is actually far more stable at the extreme ends of the noise scale. And finally, classifier 3 guidance, or CFG. This is an absolute game changer. It's the magic trick where you mix conditional and unconditional predictions to aggressively force the model to adhere strictly to your text prompt. It is the secret sauce behind almost every state-of-the-art image generator today. Section 5. Scaling diffusion for production. The original DDPM paper was a massive breakthrough, but it had a bit of a fatal flaw. And that flaw was the number 1,000. It required 1,000 passes through a heavy neural network just to generate a single image. In a production environment where compute costs serious money and users expect instant gratification, this is a massive latency bottleneck. Literally nobody can afford to ship that. To fix that major speed limit, engineers use a really clever 3-step optimization stack. Step 1. You change the math of the sampling loop. By swapping to a deterministic sampler like DDIM, you can skip steps entirely, cutting the process down from 1,000 steps to just 20 to 50. And you don't even have to retrain your model. Step 2. If that is still not fast enough, you bring in distillation techniques like consistency models. Basically, you train a smaller student model to guess the output of the big model, crushing the process down to just 1 to 4 steps. Insane, right? Finally, step 3. You deploy hardcore software engineering. You compile your model with tools like TensorRT to shave off every possible millisecond of overhead. Together, this stack turns a painfully slow academic process into real-time generation. And when you combine those speed hacks with the right architectures, diffusion literally conquers every single modality out there. For basic images, we still rely heavily on UNets. But for massive video generation models, we've swapped out UNets for spatiotemporal diffusion transformers, or DITs. Over in audio, we use encode paired with a transformer. And in the hard sciences, for things like drug discovery and protein folding, we use equivariant diffusion models. But here's the beautiful part. The core concept, destroying data with noise and learning to reverse it, remains exactly the same across every single one of them. Of course, the AI landscape never stands still, right? A new framework called flow matching is currently emerging, offering a different mathematical path that often beats traditional diffusion on pure inference speed. Which leaves us with this final thrilling thought to ponder. Is this elegant, somewhat paradoxical process of deliberately destroying data only to rebuild it the final destination for generative AI? Or will we look back on it as just a vital, brilliant stepping stone to something even faster? Thank you so much for joining me on this explainer, and I encourage you to keep questioning the magic behind the models.